So, looking at these questions, in this here, Zn, what would Zn be? Zinc. 30, I didn't even double check this. I just put what the student put for everything here. The 30, what does the 30 mean?
Was it B?
The number was the, oh boy. The correct answer is the number of protons in the atom. That's what it means. Now, remember, we talked about this before, and I forgot. If it's neutral, then the number of electrons will also be equal to the number of protons. And so when I go through and grade, if we have somebody who said the number of electrons, I'll give them partial credit because it's not specifically the number of electrons. That's not what it means. But you can infer the number of electrons if it's neutral. Okay. Yes, go ahead, Britton.
Okay, so the 65 is the mass, right?
Right. The 65 is the mass. That's because the protons and neutrons have about the same mass. Right. So within 3 significant digits, it's the same mass. And electrons are insignificant compared to those masses. We just add the number of protons and neutrons, and that's the mass. And in fact, as we'll see in today's lecture, if it says 65, that means 1 mole has a mass of 65 grams. So we have to learn what a mole is today before that makes sense. But it's telling us about the mass of one atom or the mass of a mole of atoms, either way.
So when you're given the mass, so with those two numbers, are you able to figure out how many, like, do those correlate at all? Like, if you go 65 minus 30.
Yes, that's exactly right. If you want the number of neutrons, you take the difference. Because you have the mass is protons plus neutrons. The atomic number is just protons. The difference is the neutron number. Okay, number 2. Which subatomic particle can move to different energy levels, raising or lowering the atom's energy state? It's the electrons. Okay, so what are atoms made out of? What are the 3 things they're made out of?
Ups and the down.
That was going to be my next question. The three things, the basic things, the things you knew probably before taking this class. What did we just talk about? We've talked about all 3 of them. Protons, neutrons, and electrons. Those are what atoms are made out of. And then the electrons are elementary particles. They can't be broken down to anything smaller. We call their category of particle leptons, which means light particles. The protons and neutrons, we call them baryons, which means heavy particles, and they can be broken down into quarks, up, down, and up, down, as you were saying, Brandon. Okay, number 3. Chemistry looks at blah. I thought some of these were kind of funny. Etymological. What was the correct answer? The submicroscopic. If it was microscopic, you could see the atoms in in a microscope. But they're too small to be seen in a microscope, so that's why it's submicroscopic. Macroscopic means large scale. And well, we're not dealing with ecology in chemistry class or etymology. Okay, one of my favorite nerd jokes. What's the difference in an etymologist and an entomologist? The etymologist knows the difference. Great. Okay, Jocelyn's mocking me so clearly. Okay, I think it's funny. Okay, so Na plus, what does Na stand for? Sodium, right. Why is it Na and not like SO? Latin.
Yeah.
So sodium plus bonds with F. What's F? Fe is iron. F is fluorine. Easy mistake. And you are not required to know this, right? Fe minus, what type of bond is called, or this type of bond is called an. And what was your answer?
I just guess.
Nuts.
Was ionic. I'm going to show the slide right after this to explain why. You had a question, Jocelyn? Oh, okay, I thought you had your hand up. Okay, so the types of bonds we've looked at so far were the ionic bonds, the covalent bonds. The person who put in this question also put polar covalent bond, I think. But a polar covalent bond is still covalent, so I took that out so we wouldn't have people, getting confused. Ionic bonds are the bonds that occur when one of them gives up an electron. Which one gave up an electron between these two? The sodium. It gave up an electron, so its charge went positive. Another one gains an electron, so they have opposite charges, and the attraction between opposite charges is what holds them together. So going to the lecture, the first slide here is to remind us, I was like, why is the scale off? That's why the scale's off. To remind us of this, to determine if it's ionic or polar covalent or covalent. This was the last thing I talked about in class 2 days ago. We look at the electronegativities. Fluorine has an electronegativity of 3.98. That means that fluorine really, really likes to have electrons. It wants to pull an electron to get to become F-. If we look at sodium, sodium has an electronegativity of 0.93. It's fairly weakly pulling. And so because the sodium is fairly weakly pulling, it easily gave up its electron. The fluorine was really pulling, it grabbed an electron, and then you had a positive and negative. And the problem, you didn't have to have this table to get the answer because it's told you it was a sodium plus and a fluorine minus. So you know opposite charges being held together because opposite charges attract. So that was the key to that question, that opposite charges attracting is the essence of an ionic bond. Okay, so we saw this picture last class period with the electronegativity differences to determine which one we're going to call it. No bond is perfectly ionic, no bond is perfectly covalent. Well, I guess an FF bond is perfectly covalent because they're both neutral. And so we look at the difference, and of course, if you take 3.98 minus 0.93, that's 3.05. 3.05 is definitely bigger than 2, so it's clearly in the ionic, and you see the example that was used here was what we had in the quiz question. Okay, and then I started talking about the molecular polarity, and we talked about something like this here. Actually, the two that are circled are both polar because the fluorine is pulling electrons toward it. The hydrogen and sodium are not pulling them as strongly, and so you end up with the fluorine being more negative, the hydrogen or sodium being less negative, and that makes it polar. Polar meaning you have charge that's not equally distributed. If you have something like this, see, what does it mean to have those two parallel lines? This was another question that didn't come up when the student turned in. It means it's a double bond. It means you have two pairs of electrons that are being shared between both atoms. So we have that double bond, and looking at the electronegativities, if we look at carbon, carbon is 2.55, O is 3.44. Which one wants electrons more? Between carbon and oxygen. Oxygen, because it has the higher electronegativity. That's what the electronegativity means. And I actually should have done these in a different color so we didn't confuse the two different. So that means oxygen is pulling the electrons more, so you have more electrons out here by the oxygen, less electrons by the carbon. So if you look at charge states, it's going to have a negative charge for the oxygen, positive charge for the carbon, and negative charge for the oxygen again. But that's not polar because you have the same charge on this side as you have on this side. And based on it being flat, it's just going to look like a negative object, basically. Water, on the other hand, I think this is where I ended. This is the absolute last slide from last class period. Water, with its oxygen pulling electrons, hydrogen not really caring to hold on to the electrons. Once again, going back to the chart, hydrogen, that's 2.2. That's a lot bigger than sodium. It wants the electrons a lot more than sodium does, but still oxygen with its 3.44, it's pulling them so that you have the oxygen tends to have a negative charge on it, and each hydrogen is a positive charge because the electron is spending more time with the oxygen that's pulling it more. And as a result, a water molecule is polar. It has one side that's positive and one side that's negative. Yes, ma'am.
What's the little squiggle?
The delta? That is one way of writing the Greek lowercase d. There's a couple different ways of writing the Greek lowercase d that we use in math. And so that just means a small amount of positive charge.
Okay.
The actual amount is like 0.65 electron charges, which is reasonably large. But that's what it means. So water is a polar molecule. That's going to turn out to be important as we look at the things coming up. We have polar molecules, opposites attract. So let's say I look at this molecule right here. It has a negative side. That negative side is then going to be attracted to the positive side of another water molecule. So you see that the positive side of this one here is positive, this one here is positive. Each one of those positives went to a negative. And so the water molecules form these little bonds. We call them hydrogen bonds because of the polar nature of the water molecule. And it's these hydrogen bonds that give water a lot of its unique properties. I think we talked about before, water has a unique property that it's most dense at 4 degrees Celsius. If you heat it from there, it becomes less dense. That's normal. But if you cool it from there, it becomes less dense. That's not normal. And the reason for that is when you cool it, it settles into a configuration where it's making these hydrogen bonds. But that configuration actually makes it expand, which is why ice expands when you freeze it. It also, because of the stability of that, it makes water so it's a liquid at room temperature rather than a gas at room temperature, which we should appreciate, right? So we can swim in water, take baths, all those good things. So our first clicker question. Which is heavier, carbon dioxide or water? One left. There we go. Okay, so we had 6930. So let us discuss amongst ourselves, and that means you among yourselves, of course. See how people came to their answer, how you got to your answer, and see, we'll obviously re-poll it and see if we can come to a more convincing result. Make sure you discuss how do you determine which one's heavier.
So I was just has more space.
Right.
It becomes larger, actually.
Let's see.
So they
I just if we had water, it's not right. Just be like, even if you put the carbon dioxide in first, the water would still be on. So that's gravity.
So technically, I still gas water. But I feel like the answer is carbon dioxide is always such a thing.
You're not even wrong.
Right? Because I think the answer is water, I'm gonna go with carbon dioxide.
I'm gonna go with water.
Because my guess is still on this.
Okay, let's go ahead and answer a second time.
I don't know, probably wrong, but it doesn't matter.
As long as I know the answer afterwards.
The thinking about it to see what you understand is supposed to be part of helping you learn. That's the pedagogy behind these.
Not here.
What if I literally just sat here the entire like
I'd be okay with that.
I would be laughing.
Okay, we ended up pretty similar. 7, 8, and 1. So randomly selected Larissa. Which one did you go with and what was your reasoning?
Okay, I went with A. Originally I went with B, but I looked back at the table and I saw, does that mean it's right?
Well, go on.
Oh. I looked back at the table and I saw that carbon has a mass of 12 and 2 oxygens, they're about 16. And then I looked at H2O and H is only 1, there's 2 of them. And then, like you said, O is 16. So just doing the math, I said that would be heavier because it has a heavier mass.
Okay, so she did it the right way. Yes, you did have the right answer. She did it the right way. You just take and add them up. So CO2 is going to be 1 times 12 plus 2 times 16. Let me put parentheses so it's clear that those aren't decimals. So that's 32 plus 12 is 44. So you have 44 protons plus neutrons with that. With H2O, change color just so we're H2O, you're going to have 2 times the 1 for hydrogen plus 1 times the 16 for oxygen. That's 18. And so since 44 is a bigger number than 18, the answer was indeed carbon dioxide is heavier. So you were apparently the one person who moved the right way.
Oh, I moved.
Yeah, other people could have. But the net result was one person moved the right way from water to carbon dioxide, and that's what she had moved. Okay, so good job. Yeah. Oh, let me give you a score for that just while we're thinking about it. Yeah, for the answer. Yeah. Oops, I went through 2. Different kinds of bonds. Reminder, the types of bonds we've looked at were covalent, polar covalent, and ionic. And all of those had to do with, of course, electrons. All bonds have to do with electrons. The covalents were sharing electrons between 2 atoms. The ionic was actually electron transferred, and then you had the ions having different charges. So here's another kind of bond. Can't write on that with this. The ion dipole. That means you have one atom as an ion, while the other atom is a dipole. So an example of a dipole we've seen is water, H2O. It's a dipole with a net negative on the O side and positive for the hydrogens. So if I have a sodium ion that's a positive, opposites attract, the negative from the oxygen is going to be attracted, the negative side of the water molecule, the oxygen is going to be attracted to that sodium. And so we're going to make sodium hydroxide. And the sodium hydroxide is actually it's not sodium hydroxide. Sodium hydroxide is NaOH. But we're going to have bonds that form here, pulling the oxygens towards sodium. And of course, if we dissolved salt, sodium chloride, into water, the chlorine would be attracting the positive sides of the water. And so what happens when you put salt in water is exactly that. You have a chemical transformation. It goes from being a molecule of sodium bound to chlorine to the sodium and the chlorine dissociating, and the sodium attracting the negative sides of water molecules around it, the chlorine attracting the positive sides of water molecules around it. Now, there's only a certain amount of sodium chloride that you can dissolve in water. If you put in too much, all the water will be clustered around a bunch of sodiums and a bunch of chlorines, and then you'll still have sodium and chlorine that hasn't had that happen to it, and so that part won't dissolve. So if you put a little salt in water, it will dissolve. If you put equal parts water and salt, it won't all dissolve. Only some of it will. We're going to be looking at this in the lab this week. That's a chemical change because we're actually dissolving it, separating the sodium and the chlorine. So the first step you're going to do is to check to see if your powder will dissolve in water. That should be the first step for everyone. And because water is a dipole, if it's something that can dissolve and separate into two ions, then it will dissolve. If it can't, then it won't. So that's one kind of bond, ion dipole. It's not a strong bond that's holding a molecule together in this case. It's a weak bond that's just kind of holding them together. You could easily separate them. Next is the dipole-dipole. The dipole-dipole is an example of, well, the hydrogen bonds are actually an example of a dipole-dipole, but it's where you have something that has a dipole, so it has positive and negative charge separated, and then the positive and negatives will attract, holding them once again together. So it's weak, and like I said, it's the cohesive force between water. Those hydrogen bonds are dipole-dipole. Third type, dipole and induced dipole. What does it mean to induce something? If I induce you to do something, what have I done? I made you do it. I forced you to do it. An induced dipole occurs if I have something like, let's say it is just for grins, I'm going to say a carbon atom. And the carbon atom has charge all equally distributed around it. And then I bring something up that's positive. What's the positive going to do to the electrons?
Track them.
It's going to attract them. So the charge around the carbon is going to be then distorted because of that, so that the electrons are more like this, leaving an induced dipole with positive over here and negative over here for the carbon. But then because of that induced dipole, because you rearrange the charge configuration, now you have a negative side that's closer because the force is proportional to 1 over separation squared. The closer charge is going to have the stronger force and it will hold it together. Now we're going down in strength as we go down. So ion dipole was stronger. Dipole-dipole is weaker. Dipole-induced dipole is still weaker. And then there's the really crazy, so here's an example showing an actual example, whereas mine was I just chose a random molecule. So O2 being attracted to water because of dipole-induced dipole. The last one is induced dipole. How does that happen? Well, I take two atoms that have symmetric charge distribution, so the electrons are equally distributed. If they get close enough together, I'm going to have the electrons repel, pushing them away. And so I'm going to have, if two things get close, they're going to have, the sides that are closer have the electrons pushed away, and it's going to create a dipole moment. And then I can have an actual force between them because I created artificially a dipole moment. Now, as you can guess, this one is really, really weak. Notice it says, this nonpolar argon creates a temporary dipole moment in argon. And so that can make very weak attractions between even things like argon that's an inert gas. So there we've gone through all of the different kinds of bonds: covalent, polar covalent, ionic, ion dipole, dipole dipole, dipole induced dipole, and induced dipole induced dipole. And going from strongest to weakest, it's ionic and down. So yeah, here is just that list in order of weakness for the additional ones. I already went through it, so I don't know why I need to look at it again. The strength of bonds makes some significant differences to the physical properties of chemicals. So in this table here, we see different chemicals, HF, hydrogen fluoride. How would you typify the bond between hydrogen and fluoride? Is it going to be a strong bond or a weak bond? A way of judging that is looking at the electronegativities. Well, it's not the only thing, mind you, but fluorine has a very high electronegativity. It really wants electrons. Hydrogen is kind of in between. It's going to form a polar covalent bond, but a pretty strong bond. And because of that strong bond, you have to have the molecules moving relatively quickly. Well, it's not just that bond. I have to go further. It's polar. Because it's polar, the molecules will actually have stronger traction to each other. If I had something that is completely nonpolar, like O2, O2 is nonpolar. You have two oxygens, symmetrical. Because they're symmetrical, the only kind of force I'm going to have between the molecules will be induced dipole, which is our weakest force, which means that they can easily break away from each other. So the temperature where it freezes is very, very low. You have to really slow them down for them to be held in place by that weak force. And you heat it up a little, it melts to become a liquid, heat up a little bit more, and it becomes a gas. And so the boiling temperature where it becomes a gas for O2, you see, is minus 183 degrees Celsius, which we would consider chilly. But the HF, because it's polar, it has the dipole-dipole bond, which is much stronger than induced dipole. And because of that, HF has its boiling temperature at 20 degrees Celsius. Water has a stronger dipole moment. Why stronger? Well, oxygen is not pulling electrons as strong as fluorine, but it's pulling electrons from two hydrogens. And so you end up with a stronger dipole moment, making it have an even higher boiling temperature. So that boiling temperature is related to how strong the bond is. And so polar bonds tend to have, room temperature or so boiling temperatures. Nonpolar are very cold. To me, that's interesting. Even though it's not physics, it's still very interesting.
Non-polar bonds are cold. Why?
Nonpolar bonds have a very low boiling temperature. They're not cold. To be in the liquid form, they have to be very cold because the only thing that will hold them together is an induced dipole. And that's a very, very weak force. And so temperature is a measurement of how fast they're moving. So if you have a temperature that's very high, they're just moving too fast for that to hold them together. Whereas the polar bonds, if it's polar, you have the dipole, a much stronger force. Right, that goes back to here. The dipole is here, whereas the induced dipole down here. Okay, now, this question is just an interesting question. We have a follow-up question coming up it'll probably come up in lab, actually. Is it possible for a fish to drown?
What is this?
I feel like the answer is no.
Your reasoning is strong there because I think it.
Hey, last time I was right though.
You were right by saying I think it's this way, so I'm going to choose the other way.
Yeah, I was right.
All that is learning to distrust yourself. What you need to do is to understand so you can trust yourself. Stacy, Casey, Maggie, Tiffany. What was that?
It's showing the last question.
Not to me. What'd I do? Came back. Okay, there you answered. So we have, strong here. Yes, when the water contains too little oxygen. One person said, no, because water is 88.8% oxygen by mass. It is true from there to there. Water is mostly oxygen by mass, right? The O is much more massive than the two H's. But you can't breathe the oxygen that's bound to hydrogen. You have to have O2, oxygen bound to oxygen. And so if you have too little oxygen, that's O2, well, the fish just can't get it. Now, I've always learned that the fish, they don't breathe water. I've always learned that the fish have to swim to get the water to flow through them so they can separate out the oxygen that's in the water. And of course, if the water is not moving, you have less chance of oxygen being put into the water. That's why you have little aerators in your fish tank to put oxygen bubbles in the water for them to breathe. And so this might lead to that, but it's this here that was the root cause. All right, Teflon pans. Who likes Teflon pans? Non-stick, yes. Who doesn't? My wife is with you. Teflon is a polymer. A polymer means you have a long chain of atoms that are all bound together in that chain. So it's a long chain with fluorines on it. Now, fluorine, we've been talking about, it's our most electronegative atom. It really wants electrons. And because it really wants electrons, it's highly reactive. It forms strong bonds with just about anything. And so fluorine, like elemental fluorine, is really dangerous. When I was in graduate school, I was using fluorine gas. And before you do anything with it, you have to read what they call the material safety data sheets. And it tells you about all the really, really damaging things that will happen if you encounter fluorine. And here, Teflon is mostly fluorine. And so some people get really concerned about that. But the fluorine, the reason Teflon does what it does, it's a non-stick coating, is because that fluorine is producing a non-polar, because of the arrangement of atoms, non-polar bonds, or non-polar molecules, and thus it's not really interacting with anything else. So if you eat that Teflon, yes, there's fluorine atoms, but those fluorine atoms are bound to carbon atoms and they're not going to mess with you, in theory. Now, in practice, I'm pretty sure that it's safe, but I would leave it to chemists who actually study that for a living to give you the real lowdown on what's the likelihood of there being a problem from eating Teflon that's flaked off of your plate. But Teflon works because of the non-polar fluorine atoms in that bond. So another question, I got too many questions probably. Which type of molecular attraction takes the least amount of energy to break apart? So we have the 4 different types of bonds that we've just been talking about. Which one is the weakest one, the one that's easiest to break apart?
If this was the question you wrote, should I change it? If I wrote a question that was pretty much like this, should I change it?
I think
Well,
we should keep it.
There are 2 sides to this. Your questions need to be something I talked about in class, right? I mean, I get questions from people that are clearly not things I talked about in class, and that lowers the score considerably. On the other hand, if it's an actual question I gave, then it's probably not going to be original either.
Well, it's not the same wording.
Question, Casey?
Do they have to be like, do they have to be super scientific? Because couldn't I technically use a question, does Dr. Webb like Teflon pans? Because that was talked about in class.
No, because we're talking about questions that I would use potentially on a test. And that wouldn't be something I would test you on. So yeah, that wouldn't be a useful question. So here's our breakdown. We had 12 people who said induced dipole, induced dipole. So this person right here, whose name is Brandon.
Yeah.
What'd you choose?
Well, I chose D. Look at you.
And why'd you choose it?
On the little chart that we wrote down, it said that induced dipole were the weakest
Okay.
bonds, and so they wouldn't require that much energy.
Because they're the weakest, they are, surprisingly, the weakest. Right, that's what it's asking, which one's the weakest, which takes the least energy to break it apart means the weakest. So, good job. Now, moving on to chapter 16. Hey, we got 10 minutes. That's why we're going to have to talk some more about this when we get to lab tomorrow. So we're going to talk about mixtures. In lab, we're going to have chemical tests to try to determine what is in each material. And in some cases, we're going to have changes in the physical composition. That is, like with sodium and chloride and water, they will separate, and so that's a physical change. Or excuse me, that's a chemical change. In some cases, we're going to have chemical changes and some physical changes. So when we start talking about mixtures, we have different names for different types of mixtures. So first, a pure substance. Pure substance, it's all the same thing. So only one type of element or compound. So you can have pure water, only H2O. Pure gold, only AU. A mixture is a collection of two or more substances that can be separated by some physical means. So you might put them in a centrifuge, you might put them through a filter, some way of separating them. Here is sugar, another one of the things. By the way, let me point out right now, there is a typo on the lab guide. The third page where it has you put down which one you thought was table sugar. It has table sugar listed 2 places. The second place should be table salt. So keep that in mind. Also, remember I told you to make your little test algorithm before you come to lab? Just put that test algorithm on the blank 4th page of the lab guide. Question?
Can you answer a question about the homework?
Oh, right. I forgot to do that. Actually, Larissa asked first. So what was your question? Hopefully it's the same one.
It was the one that was like, how do you know when you know something? Super famous.
Okay. Is that what you're asking about, Sissy?
No.
No. Okay.
Am I like an opinion question?
Hmm?
Am I like an opinion question?
Well,
It's in the comments.
A word?
Yeah. It's a little thought bubble.
Or there's a fumble.
Yeah.
it is a good question for education students especially. Because, you know, if you're working with children and trying to teach them, I want you to think about, you know, how can a person really gauge how well they
I
understand?
just wasn't sure if it was like an opinion or if you wanted like a specific, because if it's opinion, I can elaborate on that. But like if it's like if you're looking for something.
I do want you to match what the textbook is talking about on that. Because, I mean, there are different ways of knowing, you know, connected and whatnot. The key to that question is something that I always talk about when you're studying with somebody else. If I study with Casey, because her hand was up, if I try to explain something to her and I can't explain it, what's that going to mean?
You don't really know.
I don't really know it. I have an idea, but I don't really know it. But if I can explain it to her, I must know it better. So what question did you want to talk about, Stacy?
The uranium, explain the uranium.
Okay, explain the uranium. Let me just go back to, not that one. It should be this one here. Okay, so go back to the last lecture's PDF so I can find the figure that's involved with that. We'll get there. And we passed it. Where was it? Oh, maybe it was 2 lectures ago. Crud. Yes, open it. Living life on the dangerous side now. This is the quicker way to check to see if the graph is in it. Nope, I don't see the graph here either. Must be one further back. Because you do have to go to, okay, that should do it. You do have to go to the picture to understand it. For the one involving uranium, yes, there's a picture. Here we go. There's 3 different versions of it in the lecture. I'm going to choose, not that one. This one here. Now, I marked it all up because I talked about the fission and fusion when I was lecturing on it. So I'm going to delete all my marks here and all but one of them. Start over. This graph shows the mass per nucleon. Remember, we learned that the mass of a proton is different when it's by itself compared to when it's in an atom. And different atoms, you'll have different mass changes for the proton and neutron. So that it turns out that the masses of protons and neutrons are the lowest in iron. And the mass of proton is the highest when it's by itself. And so we start with uranium. So we're starting out here. And it says, okay, if we break it into 3 even pieces. So if we break it into 3 even pieces or 2 even pieces, 2 even pieces means that we're going to break it into 2 pieces that are halfway between the beginning and end of this graph. So we're going to break into 2 pieces that are about there. That's about breaking it in half. Breaking it into 3 even pieces is going to be about a third of the way. So that's going to be something like this. And then breaking it in 92 pieces is all the way over here. So we can see where the mass per proton is for each one of those options. So here is the mass per proton that we start with. And we want to compare it to the mass per proton for each one of these. And if the mass per proton decreases, if the protons become less massive, that means energy was released. And so energy being released, well, that's what we were looking for. Which one releases the most energy? So all you have to do is say, well, if I go from, and I should write numbers here just to make sure people are clear on what I wrote. This is breaking it into 1/2 the size, this is breaking into 1/3 the size, and this is breaking into 92 equal pieces. If I break it to 1/2 the size, did it go to a lighter mass or a heavier mass? Remember, this is the mass per nucleon. So it went lighter. Does that mean that it gave up energy or it absorbed energy? Gave up. So when I look at these, I say, okay, that gave up energy. That gave up energy. This one here, it had to absorb a lot of energy. And so you're going to rank them by which one gave up the most to which one gave up the least / absorbed the most. Now, this graph wasn't part of the question. It's how you answer it. Right? People were shocked. Oh, there's supposed to be a picture. It wasn't supposed to be with the question. It was supposed to refer you to, looking in your textbook, and you answer by that. Okay. Did you have a different question?
Oh, mine's the same.
Same. Okay. Then since we are